So today's lesson in AP Calculus AB is Euler's method. Euler's method is named after Leonhard Euler, who lived in the 1700s, and he was the dominant mathematician of his century, the most prolific mathematician ever. Was also an astronomer, physicist, botanist, and chemist, and an expert in Oriental language. His work was the first to give the function concept the prominence that it has in mathematics today. So the function concept, that was his. Euler's collected books and papers fill 72 volumes. Euler is actually Swiss, although a lot of his stuff, his introductory algebra text was written in German. Okay? So Euler is Swiss. It's not Euler, not the best of pronunciation, but it's not Euler. It's more like Euler, like the hockey team, Euler. That's sort of how it's pronounced. All right, Euler's method. Well, what is Euler's method, and why do we need to learn about Euler's method? Euler's method is a way of solving differential equations, finding the functions that differential equations represent. So it has to do with differential equations. And if you remember in the past here, we've been working with differential equations. First of all, what we did was we used the slope fields to graph, right? So if you remember something like this, if we had slopes like this, and then slopes like that, and then it went like this. Remember all this? Quite sharp, sort of thing. So if we were to use a slope field, we would sort of generate, well, you have some sort of function that maybe looked like this, right? Generated by those slope fields. Because at each point, you know what the slope is, but you don't know what the function looks like. So you kind of piece that together. Then we went to, so this in red here is the function that we're looking for, right? Sort of the solution to a differential equation. What's the function? Then we talked about slope fields, and then we talked about separable differential equations. So separable differential equations. And that's, of course, where we did dy over dx equals something like, let's just say x. And you kind of got all the x stuff on one side and all the d stuff on the other, right? So remember we separated them, separate, and then we went on from there, integrating both sides, and so on, right? So doing this we also got actual representation for f of x. What our y would be, our f of x would be. And actually, for this lesson, I'm going to change this f of x. I'm going to start writing things in y of x, because the differential of y, we're looking for the function of y, right? So I'm going to put y of x instead of f of x. But, so this is graph method right here, the slope fields. We were able to graph it. This actually gives us a nice full equation, but in many cases, we're not able to find the answer, the function, because this differential equation maybe is very complicated. It's not separable. It's really, really difficult to do, or it's impossible to find just from the differential equation itself. And so this is when we use a method called Euler's method, and it's really a method of approximations. So our third option here is to basically use this method that Euler came up with. And what it does is it uses linearization. So we talked about linearization, right? And how we can approximate things. And if you don't know about that, Newton's method, linearization, that sort of thing, we did a lesson on that. So you may have to go watch that again if you don't know what that is. But we're going to use that concept here to make approximations. So to approximate the function y of x. So given the differential dy dx, okay, equals something. And actually, this something for the purposes of this lesson as well. Um, uh, so more or less like this, right? So the derivative of x, y, because there's going to be x and y usually in there. So that's kind of what that is. So our y of x, this y of x, is actually going to be, just some function of x, y. Does that make sense? You have the derivative, and you've got your parent function. So we're going to approximate this. That's our big deal here. We're going to approximate it. And linearization, the method that we looked at before, is what we're going to do. We're going to do this. Okay, so again, so we have a bit of a background here, differential equation. So Euler's method is a numerical approximation. We're not going to find the function. We're not going to just kind of make a graph. We are going to approximate points that would be very close to what the function would be. Not exact, but very, very close. And the method is quite clever, and we're going to go over it here now. So let's just say that we have a collection of slopes like this. Okay, we have a collection of slopes. And if we talk about a slope field, this is sort of what we have, right? They're all over the place. But let's just pick a few here. Now, I could say, all right, these are the points on my graph here, right? And this is my solution here. It's going to look like this. This is the exact solution. Okay? That's a bit off there, but that in blue is going to be our solution. Now, the thing is, when we're trying to find that, we don't know what that graph looks like. We don't know the definition of it. We don't know what these points are. But let's just back that up now and say, hey, I'm given all of these slopes, and I want to try to approximate that graph. So here it is. Now, if I take a look at this red line here, this slope 1, okay? So slope 1, this red line. You remember with linearization, what we did was we used the tangent line to say, all right, if I just kind of went from this point and I stayed on this tangent line, another point that's just a little bit to the right or to the left, we always used it to the right, but just a little bit to the right would be pretty close to where the function would be. See how that's really close, right? And over here too, let's say, we followed this tangent line over, and this point would be pretty close to the actual point on the graph. That's exactly what we were doing. This one, well, let's do, some of these aren't very good. Let's do this point right here, okay? It doesn't actually touch, but let's say it touches right there. So if I used the tangent line and just kind of went over a little ways, right? Just a little ways over here, this would be pretty close to where the tangent line would be. So if I got rid of this line, those blue dots right here, the big fat blue dots here, would be pretty close. This one, you see that's pretty close. It mirrors pretty close to what the original graph is. So that's what we're going to do. That's really what we're going to do. We're going to piece it together, though, from an initial condition point, and then we're going to do this sort of linearization. We're going to build the points to what would be a mirror or an approximation of what the graph is going to be. So we're going to be given an initial condition. So let me just clear this up a little bit. We're going to be given an initial condition, and let's say it's something like this right here. And we're going to be given the definition of the slope, which is the differential equation, right? dy over dx. And let's just, it's something, whatever it is. But this is going to be the slope, once we put x and y in, it's going to be the slope of the tangent line, right? So if we consider the tangent line to be something like this, I could easily find a point over here, or anywhere on this line. And how do you do that? Well, if you recall from your basic math that between any 2 points on a line, you have a rise, delta y, over a run, delta x. That's what the slope is. So this right here, this slope is really delta y over delta x, right? The rise over run. And that's what that slope is. So if I wanted to find out how what this point was, or basically this delta y, like how far up do I go, where do I place this point, the delta y, this change, if that's something I was going to solve for, would be dy over dx times delta x. Okay, so you could manipulate that equation. And so how far up do you go and how far over do we go? We're going to be able to piece that together to place another point. Okay. Now this delta x is going to be a fairly arbitrary distance, and you can probably imagine that we're going to have a little bit better approximation if delta x is small. Right? The smaller delta x gets, so let's say this is a delta x right here. Okay, steps like this, or whatever it is, right? If I had smaller steps like this, I would probably get a better approximation with more points in a smaller area. You see that? So instead of the graph looking like this, maybe the graph actually looks like this, and I would get a much better approximation using a shorter distance of delta x. So we're going to choose a step size is what delta x is. We're going to choose how far over we get. And what you want to be thinking is, think of Riemann sums too, right? The wider those rectangles are, the less accurate it's going to be. So the narrow, you want to narrow that up. So it's all related here. Okay, so to get the next point, delta x is something that we choose. We choose a random distance between x's. But to get the next point, all right. So let's just maybe formulate. Let's write some of this stuff down. Yeah, we're drawing some pictures. Let's write some stuff down. All right, so given an initial condition, that is an initial point, like this point right here, we can use the slopes of the tangents to approximate. Now, slopes of the tangents, that's defined by dy or dx. We can use those slopes and the point that we're on to generate other points that would approximate our new curve. Since we know that the change in y, that's the vertical change, is given by the slope times the change in x, the next point that's generated, that is going to be y1, will be our original y value plus this rate of change over a period. So it's going to look like this. Up here in the graph, here is x naught, or x sub 0. This is y sub 0. Right? That's the initial condition. Now to get this next point right here, right? This is x sub 1. This is y sub 1. To get that next point, we have to consider our delta x here, right? And our slope, the slope of our tangent line. And we can generate y1 using this formula right here. So this process is what Euler's method is. It's generating points. We have x, y, then we have x sub 1, y sub 1, then we have x sub 2, y sub 2, and so on. And these points, using this method, will be points that, when plotted, will give us a good approximation of what the curve is, the actual y value is. So let's do an example, and I'll show you a chart. We're going to use a chart. Instead of a big, gross formula, we're going to use a chart. I'm going to show you how to kind of work this through. Right? So here's our example that we're going to work through here. It says, use Euler's method to approximate the function y at 0.3. Okay, so we're talking about our parent function at x equals 0.3 for the initial value problem of, and here's our differential equation, dy dx equals x plus y, given the initial condition of y of 0 equals 1. So that is x naught equals 0, and y naught, y sub 0 equals 1. That's the initial conditions. All right, so this is the way I'm going to encourage you to set this up. Make a x column, make a y column, and also make another column that includes how to determine your new y value. Okay, so it's going to look like this: y plus dy over dx times delta x. We're going to work this out over here. Important to note that dy over dx, according to this problem, is x plus y. X plus y. So this x plus y is actually what this is. Okay, and we're going to show that here. How do we work this out? So first thing you want to do is you want to put your initial conditions in initially, right? So x is going to be 0, y is going to be 1. What I would suggest you do is to fill then in the x column, because this is what we want. We want to find out when x equals 0.3, what's our best guess using this method as to what the y value will be, right? That's what we're asking. This is the y value when x equals 0.3. So down here, we're going to have 0.3. That's what we're going to get to. And the increments, the step size, the incremental size of delta x, we're going to change by 0.1 each time. So we're going to have 0, then we're going to move to 0.1, then we're going to move to 0.2, and finally then to 0.3. So my suggestion would be to fill in this x column using, find out what the question's asking, using the step size here of 0.1, and then of course your initial conditions go there and there. Okay, so how do we fill out this chart and how do we solve this problem? Well, we know that x and y is 0 and 1. Let's fill in this one here now. So we're going to start off at our given y value, which is 1. It's right there. You always use the same value right there. So there's y, there's y. We're going to add to that, okay? So this is basically our delta y now, right? So y plus a change in y. How do we find that? Well, we put in our x and y value, that's 0 and 1, over here in our dy over dx, 0 plus 1. And of course, that equals 1, right? So dy over dx for our first row is 1. Make sense? Times our delta x, which is 0.1. It's going to be the same with each row. So this is 1.1. So our very next y value, think about what we're doing here. So 0, 1. We're using the tangent line, the slope of the tangent line, which actually is 1, right? And we're using a very small proportion, and we're placing this point right here. That is this y value. Okay. So this 1.1 now goes into the next row. So what did we do? Here, our delta x, we changed from 0 to 0.1, and we calculated our delta y right here, and added it to our original y to get our new y value. And then we repeat the process now. So now, the next step, I'll use a different color here. So now we got 1.1. So to find our next y value, we go 1.1 plus. Now, what is the derivative at this x value of 0.1? So let's go try again. So it's going to be, now it's going to be 0.1 plus, what's the y value? 1.1. So that's going to be 1.2, right? So this is 1.2. And then times delta x, of course, is 10.1. And that for an answer should then be 1.22. So that's our new y value, and that's the y value then at this next point. So look at what we've done here now. So we've got a little bit of a different slope. You see in red here how I'm using a little bit of a different slope now? It was 1, the blue. The red now is 1.2. So now I'm using the same step size, but I've got a little bit of a different y value point there. You see that? And so now we have at, there's 0.1, there's 0.2, there's 0.3. So at 0.2, I have now 1.22. That's my approximation. Good? Okay. So let's do it one more time. So 1.22 plus, all right, what's dy over dx at this x value? Well, should I use a different color? Yes. Let's go back to what? Let's do yellow. So my x value, I said, was 0.2. My y value is 1.22. So what's that? 1.42? Wait, what? Yeah, is that right? So this is 1.42 times 0.1. And Do you get then 1.362? Yes? Good. Okay, so then 1.362 is our best guess for x equals 0.3. Now that's exactly what we were looking at. So this right here is our answer. Y of 0.3, 1.362. That is our answer. Okay, so if I just were to finish this off here over here on the diagram, so then I have 1.42, so at this x value, okay, so 1.42, so here's our slope at this one, and then at 0.3, here's my answer there, 1.362. That's not to scale or anything, but that's how we're generating things here. Okay? So that's a bit of an introduction to Euler's method. I am going to, and there's the example. What I'd like to do just to finish off this little lesson here is to kind of explain to you sort of what the formula is, what the explanation is for Euler's method, given this, given what we're doing here. So let's just finish off with that. Now, given that dy over dx, okay, is going to be what I say earlier, this right here, x, f prime of x equals y. Okay, so we are generating points, x, y points, where this point that we're going to end up with, so the last point, the x value that you want to end up with, so that's the last one in our chart up here, right? That's going to come from doing this, taking the x value just before that, x sub n minus 1, plus delta x. That's how you get your x value at the for any row in this table. The y value, so y sub n then, is going to be y sub n minus 1 plus the slope here at these x and y values. So it's basically this, the derivative, right, evaluated at x sub n minus 1, y sub n minus 1, and this is where it gets a bit tricky, times delta x. So you should be able to understand that, hopefully, but that's how you get any x, y value pair in the row. And just what I'm going to do here is I'm just going to move this off to the side here, so it looks like this part's but it's actually not. Whoa. Okay, it's changing size on me. That is weird. Oh, there's a demon here in this video. Sorry. Ah. So now it's super huge. That is hilarious. Okay. Let me fix it. All right, there we go. So we got it fixed up. So yeah. So that's Euler's method, and I really like this table. Okay, in the textbook you'll see something just a bit different. They've got many columns to the table, but I think this is really all you need. Okay, and remember, initial conditions go here, and your step sizes go here. So you change whatever your x value is. It's not always going to be 0, but you always change it by the predetermined step size until you get to the last row, right? The last x value, and then you simply work on y using your differential, and you generate new y values each time, and there you go. It works pretty slick. So this is for first order differential equations, right? So just first order, and that's Euler's method. So that's kind of the third piece to this puzzle here. Slope fields, take a look at those. Separable differential equations, we were able to actually solve for a function. This one now is approximating points that would make up that solution function. Euler's method.